So I want to try something. I don't normally do this. This is from Veritasium's channel, who has great stuff. Everything is super great. And he showed this video based on a problem of a helicopter moving with a rope hanging below it, and what would the shape of the rope be. And I think I originally got this wrong. I want to show you he actually did it. That's pretty awesome. So here's a helicopter, and let me just play this. If I can play this. It's moving, and the cable's straight, which I wouldn't have guessed. I would have guessed it would have curved like that. But that's all fine. It's all good because I want to model this. So how would you model this situation? Now, cables are kind of hard. So here's the cable, and his explanation is that down here, if you just look at that part of it, there is a gravitational force pulling down. There's a backwards pushing air resistance force, F air, and then there's a tension pulling up. And as you increase the size of that, all those parameters change the same. And I get it, and I see what he's doing, but I have this feeling like if the size of the cable, I think the linear cable density matters, and I'm not sure, okay? I'm not even sure this is gonna work. Then it wouldn't take that path. I think if you had like a really, really light cable, it might not work. So I don't have a helicopter. I'm not gonna rent a helicopter. Not now. So I'm just gonna model it. So how would you model this moving cable? Okay. First, how do you make a cable? This one's a little tough, but let's say I have a surface up here. One way to make a cable is to make use masses and springs. So here's my model for a cable. I'm going to have a mass, a spring, a mass, a spring, a mass, a spring, a mass. That's good enough. And especially if this is really, cables aren't completely stiff. Cables have a spring to them. So if these are stiff enough, I can get this to model a string. And so this is 1, 2, 3, 4 masses, and 1, 2, 3 springs. But if I can set this up for 4 masses, I can set this up for 100 masses. It's the same thing. Okay. So on each of these masses, there's going to be some forces. There's going to be the gravitational force, where G is the downward vector, the gravitational field, negative 9.8, 0, 0, and M is the mass of each piece. Okay, so let's say up here, I'm going to say N is equal to 4, and the mass is equal to 20 kilograms. Then the total mass. Then the small mass would be the big mass over N, and I can find that. I also need the length of the whole thing. I'm going to say that's 5 meters. So the length of each piece is actually going to be equal to, I'll call it DL, and I just realized I was thinking about this wrong, is going to be the total length divided by N minus 1, right? Because if this is 1, 2, 3 pieces, if I have, I'm sorry, I was using N equals 4, N minus 1. Of course, if I have a really long spring, it's not going to matter, but there we go. So I have the gravitational force, and then I'm going to have a spring force. So if I have a spring like that, it has an unstretched length of L0 and a length vector of L. Then the spring force, I can say Fs is negative K L minus the magnitude of L0 minus the magnitude of L times L hat. So this says that if the spring is stretched over here, then the magnitude of L is going to be greater than the magnitude of L0. The spring should be pulling back that way. So I have L0 minus the magnitude. This is going to be L0 is going to be a negative number. So I think this is plus. I always get this wrong, and I'm going to get it wrong today, and it's easy to fix so. But this is a scalar value, because now what if I move the spring down here? My string is going to move. I need to include this L hat, which is the direction of the spring, to find the direction of the force. So it's going to have spring 1, Fs1, and it's going to also have Fs2, 2 springs, right? This has a force pulling up, a force pulling down from the spring below it, a gravitational force mg, and then finally it's going to have a drag force. So if my helicopter is moving this way, there will be a backwards pushing air drag, F air. And we can say F air is negative 1/2 rho a c v squared v hat. So this is the density of air, which is 1.2 kilograms per cubic meter. This is the cross-sectional area of the sphere, which that's the parameter that I think is going to change. C is a drag coefficient. C is about 0.47 for sphere. I don't have spheres, but I don't think it really matters. We can again play with that too. Now I'm going to have to add another force on here. Maybe not. I might have to add another force, another drag force that just prevents it from. I think it might be okay. I'm just worried if I have these 4 forces, 1, 2, 3, 4, it may just shake around forever. But that drag force might make it stable. And if it doesn't, I'll just add in an extra force based on a viscous drag force, depending on the momentum relative to. Yeah. Oh no, we'll have to, because this. I'm gonna actually not move this. I'm gonna make it in the wind. Let's just make it. Okay. So let's jump in here and start making this thing. It's going to be a little complicated, and I have a feeling I might stop this program and bail. But you never know what's going to happen. You never know. Okay, so I have an empty program. So I'm going to do this in Python. And let's see, can I make that bigger? Let's make that a little bit bigger. Okay, so the first thing I'm going to make is... let's see, moving my windows around over here, just so I can see stuff. Okay, the first thing I'll make is, let's just make G. That's always the thing I like to start. And I'll put comments in here later maybe, but let's say G. I know I'm going to need that. That's the vector 0, negative 9.8, 0. Now I'm going to add in, I'm going to put the parameters like the total mass. M equals 20, L equals 5, N equals 5. That's the number of pieces I'm going to break it into. So if I do that, I can say M is equal to M divided by N, and then DL is going to be the length of each piece. It's going to be my L0. That's going to be equal to L divided by N minus 1. Okay, what else do I need? I need the spring constant. K equals, let's say, 500. That might be too small. If I have, I'm trying to think if 500, let's just put, that's fine. That's fine. Okay, let's first start off, and I'm just going to make my balls. Okay, now, since I'm going to be dealing with like maybe 100 balls, I need to do this as a list. So I'm going to say balls. Let's call it B. I like short. B equals an empty list, and I'm going to go through and I'm going to add balls to that list. So I'm going to do this and I'm going to do it false first, just so you can see how it works. For I in range N, print I. So this will go through I from 0 to N. I'm going to print it just so you can see how this list works. And so I get 0, 1, 2, 3, 4. So it is 5 total things, but it starts at element number 0, and that's fine. So what if I wanted to add that to a list? I could say B equals B plus I. And then I can, after the loop, I can say print B. And B are my balls. So you see now I have a list of 0, 1, 2, 3, 4. I can print that first element in the list, B 0, which happens to be 0, with the indices 0, just like that. And I can print the last one with minus 1, just like that. Okay. So I don't want a list of numbers. I want a list of spheres. So let's say I'm going to put up here R start equals vector 0, 0, 0. I need some place to start. So I'm going to add a sphere to this list. I can make a list of spheres. Sphere, the position is going to be equal to r start plus the vector 0, negative I times dl 0. And so think about what that does. That first I is 0, right? So I'm going to be multiplying 0 times that length, and I'm going to add it to 0. So my first ball is going to be at r start. My second ball is going to be, I'm going to move it down a distance dl. The second one, I'm going to be moving it down 2 dl, and so forth. Okay, now I need the radius. Radius equals, let's do this as L divided by R factor, because I think I want to change the radius some. So I'm going to say R factor is the ratio of length to the size of the ball. R factor equals, let's say 20. So it's 20 times the smaller. We can change that. Now some other things I want to do. Let's put a comma here. Let's put the radius. This is the color. Color equals color.yellow. Do I need anything else? The momentum. I definitely need the momentum. I need the initial momentum because I'm going to use the momentum principle to update all the things. So let's say P equals vector 0, 0, 0. And I think that's it. Let's just run this and see what happens. Check that out. I have 1, 2, 3, 4, 5 balls. Okay, and they're not connected by strings. I'm going to make the strings too. But there you have it. You know what? I don't even need to make strings. I'm not going to connect these by springs. I mean, it could, but I want to get this done. I can make it better, but you see up here, if I change n equals to 20, you won't even see the strings anyway. See, and that could change the scale factor to something like smaller, 30. So then I have a bunch of balls, and they're not actually connected, but they're not actual balls anyway because it's all in a programming language. So we're cool. Okay, so let's go back to n equals 5, just so it's easier. Okay, I have my balls. They all have momentum. So what I need to do is go through each ball, calculate the net force, and update the momentum, update the position, update time. That's what I'm going to do. Okay, I do need some other things in here. I need C equals 0.47, rho equals 1.2, V equals how fast is that helicopter moving. Let's say it is 20 meters per second. So that's kind of fast. Let's say 15 meters per second. Okay. Now I need T equals 0, dt equals 0.001. Let's do that. Okay, I'm first just going to make the thing hang and see if it hangs down. So let's say while t is less than 5, rate 1,000. So this is going to do no more than 1,000 calculations per second for 5 seconds. Okay, the first thing I need to do is to go through and calculate the force on each ball. And I'm going to, just to make my life a little bit easier, I'm going to make a list of forces. So I'm going to go up here and say F equals an empty list for I in range N, F equals F plus vector 0, 0, 0. So what that will do is it makes a list of 0 vectors, so each vector can represent a vector on each ball. Yeah, I think so. I got DL. I got the mass, lowercase mass, which I could associate with the thing, but I think that's good. I'm just looking at my notes here. The drag constant, I got that. The momentum, okay, they're all 0. Okay, so let's do it. Let's first calculate all of the forces. Now you see I do have a problem here, because this top mass up here, the very first one, I want it to be fixed. And I, just to be clear, I'm not moving my chain, I'm moving the air, so it should be the same thing. The last mass is different because this only has one spring acting on it because there's only one mass above it. So every other mass is the same. This one has, let me run it with 5 just so we can see. So this one has 2 springs, this one has 2 springs, this one has 2 springs. That one has, I'm going to keep fixed, and that one only has 1 spring. So what I want to do is just go through these middle pieces. So let's do this. Let's say for I in range n minus 2. I am looking at my notes a little bit because I will make a mistake. The first thing I want to do is to calculate the vector from this mass up and from this mass up. I'm going to call this one R1 and that R2. So I'm going to say R1 equals B. And remember, I'm starting at I is equal to 0. So I want to go down 1, which is adding 1 to the index. The top one is I equals 0. So I'm going to say B I plus 1. That's the position of this mass, the second mass right there. And then I'm going to subtract the position of the first mass. So this is going to be final minus initial. So I'm drawing the vector up. So it's going to be my dot POS minus B I dot POS. And that's my vector R1. Now I need to find vector R2, which is down below it, which is going to be equal to, so these are both downward pointing vectors. It's final minus initial. R2 equals B I plus 2 dot POS. And remember, B of I plus 2 is a sphere. So it does have a POS parameter. B I plus 1 dot POS. So all I've done is just find the length of those vectors, and I'm going to need that to calculate the force. Okay, so now I can calculate the force Fi plus 1 is equal to, it was 0, right? But now it's going to be equal to K times DL minus the mag of R1 times norm R1. And I may get that backwards. Okay, but let's just think. So DL is the unstretched length of that spring. Let me get this. One more space. Mag R1 is the magnitude of that vector, and then norm R1 is the direction of that. Now I need to do the same thing for the bottom force, but that vector is pointing down, right? They're both pointing down, so I need a negative sign on this one. So it's going to be negative K times DL minus mag R2 times norm R2. And I'm scared. I'm already scared. And now I need a gravitational force, so it's going to be plus m times g. And I haven't added in the drag force. And those are all my forces. So that's fine. That's it. Okay, so now I have the forces on all of the middle pieces. Now I need to do the last one. So let's do this. I can't remember how this works. If I have, okay, the last piece will be f of n minus 1. So I can say f n minus 1, or no, I can say n minus 1. No, let's say n minus 1. No, let's say minus 1. Yeah. Equals, now in this case, I only have that top vector. So I need to calculate this R1 and R2. Again, actually I don't, I just need to calculate R1. So R last is equal to, I don't know why I made that separate. It's going to be the bottom mass, which is going to be B minus 1 dot POS minus the one before it, which is B minus 2 dot POS. So this is going to be equal to K times DL minus mag R last times norm R last plus M times G. And now I never changed that first force, so I'm going to leave it at 0. Okay, so now I should have a list of all the forces. Now I can go through each mass and update its momentum and update its position. So I'm going to say for ball in B, and this will go through each element in there and call it a ball. Ball.P equals ball.P plus, oh, I can't do that. Let's just use, I was trying to be cool, and I failed. For I in range, let's just go through all of them in. So bi dot p equals bi dot p plus fi times dt. Now I need to update the position. bi dot pos equals bi dot pos plus bi dot p times dt divided by m. And I think that's it. Update time, t equals t plus dt. I don't know that this is going to work, but let's just see if it works. I mean, it looks like it's working to me, which is amazing. It's a little stretchy, but we can change that. Okay, now I'm going to add in a drag force, and then we'll increase the number of pieces. And I'm kind of excited that this is even partially working, to tell you the truth. Sometimes I even surprise myself, if you know what I mean. My window's blocking. Let me move this up here. Oops, not move that up. Let me move this up. Sorry. Okay, let me run that again. So you can see that it's not getting out of control. It's oscillating up and down, and I think that's legit, and I'm kind of excited. Let me save this thing. Helicopter cable 1. Might make another one, so let's call it 1. So now I just need to add in a drag force. So I know the velocity. This is not going to be hard. Right? I've already calculated the force on all of the pieces right here, except for the first one and the last one. So I can just add to this. Let's just say minus 0.5 times rho times, I need to calculate A. Let's put it as A. A times C times, I'm actually going to multiply this by the magnitude of bi plus 1 p divided by m, and then square that. And then multiply by the norm of bi plus 1 dot p. Okay, and I don't have an a in there, so it's not going to work. So up here, I can just do it one time, really. So if my R factor is 30, then we can say, I'm going to say this RR is L divided by R factor. So A is going to be pi times RR squared. Okay, so now that should work. Now I need to do it for the last one. The last one doesn't have a drag force on there, so I need to add that in there manually. So I'll just say the same thing. Minus 0.5 times rho times A times C times mag ball -1 for the last one dot P divided by M, all of that squared, times norm. Ooh. Aha. It's the velocity of the ball. with respect to the air. So if the air is moving that way, the ball can be moving up or down. I could just use a constant horizontal force, but that's not going to damp the vertical motions. Okay, let's find norm v. No, ball I dot v, which I have not made yet. Okay, so let me go over to the paper real quick. I still feel like this is not going to work, and I'm going to end up deleting this whole video. So I'm just letting you know where I'm at. I'm just trying to be honest with you. Okay, so let's suppose that I have the air is this way. So V air is equal to negative, it's going to be negative V 0, 0. That's my V air. And then my ball is moving this way. This is the velocity of the air with respect to the ground, so VAG. This is the velocity of the ball with respect to the air, right? Because I'm moving with the air. So, but I want the velocity of that's the velocity of the ball with respect to the ground. So, if I add these two together, yes, then I'll get the ball with respect to the air. I think that's right. So V ball is just going to be V air plus P over M. I don't know if that's going to work. It's okay to doubt yourself. I mean, that's how we make stuff. So let's go up here, and when I make the ball, I'm going to add in a new property. Let's call this VA. VA equals vector negative 15, 0, 0. And then when I make the ball, I gave it a momentum, but I'm also going to give it a V. And this V is going to be P Can I do that? Can I say P in there? Well, that's fine. Let's just say it's vector 0. Let's say it's VA. For right now. I'm going to go through it, and I can change it. That's all the balls. Okay. Now, down here, I need to update that. So, let's just say for ball in balls. No, in B. Ball.v equals VA plus ball.p divided by m. Okay, I think that works. And so that's my momentum's going to change all the time, so it's going to change my velocity. Now down here, I can use, instead of ball.p divided by, I'm just going to say ball.m.v. Yeah, and the same thing over here. Okay, and then so over here, I got the ball.v, I got to change this to ball.v. Whew, if this works, I tell you what, it's not going to work. Okay, let's save it and then run it. I don't know if something's wrong. Aha. Ball.length, undefined object, ball.length. Undefined is not an object. Okay, what did I do wrong? Oh, I. This should be -1. I can't take the... Was that it? Let's see. No. Object evaluating ball length. So something with the ball. So where do I have a ball? For ball in ball. ball.v equals VA plus ball.p. Let's say for ball in B, print ball.v. Let's just try that. Okay, I did that. So that's this. And let's print it down here. Because, I mean, I don't have balls in a lot of places. Let's see if it got past that. Print test. I feel like I'm making a super stupid mistake. It got past that. Okay. So that's not the problem. Where else do I have ball dot? Oh, that's why. B. Okay. Oh, look, it's working, but it's going the wrong way. Oh, I put. That's fine. Okay, I'm kind of excited, kind of very excited. This is crazy. Let's increase the number to 20. Let's just do that. Okay, so it seems like it's stretching a little too much, right? So I can fix that. I can fix that by making the spring constant. And in fact, my spring constant is messed up because let's say I want my whole string to be a certain value. The more pieces I put in there, it should depend on the number. But for right now, let's just put this at like 2,000. Let's just temporarily fix it. Now, it does swing back down. Oh, wow. Okay, it stopped. Let me run that for a longer time. And let's put more balls in there. 40. I can't believe it. Wow. Derek was right. I don't know what to say. I can't believe that this program came together in this amount of time. I only did it in 30 minutes. So, okay, I'm gonna stop here because it's already a long enough video. But here, let's make a good thumbnail. That's probably not that good. Okay, that's good enough. So, I really am surprised, and now I just need to come up with a good title with this. But yeah. Modeling stuff. Springs are the answer. Oh, I didn't do what I wanted to do. Let me try that really quick. What if I make this R factor really small? So what if I make the radius much bigger or the mass much smaller? Let's just make this mass 2 kilograms. Let's just see what happens there. Okay, that's important, right? Because that makes sense. If the linear density of the string is less, then it's gonna hang at a much longer, a better angle, but it's still straight. I'm just upset that I was so wrong, but my intuition was wrong. But this agrees with the video, and I just say whatever. Now, we could do something, and I'll leave this as a homework. What if that you put an extra mass at the end? Because Derek did that, and you can do that too. So I'm going to give you the code down below, this code in the link down below, a link to Derek's video. You should watch that. That's really awesome. And there you go. I'm stopping.